Good afternoon and welcome to this webinar with the title Demonstration of an Interlocking Design Automation Solution, hosted by Prover. Before I hand over to today's speaker and presenter, I just want to inform you that you have a chance to ask questions during the whole webinar. There is an icon in the GoToWebinar control panel with a question mark. So try to find that, and if you click on that, you can type in questions and we will see your questions, but the rest of the audience will not. So please ask questions when you have questions during the webinar, and we will pick them up and answer them in the end of the webinar. Okay, so if you have problems to find the control panel or find the question mark icon, it might hide away behind some windows there on your PC or on your mobile device. So look for that and type in your questions. So I'll hand over to today's speaker and presenter, Mr. Jesper Karlström from Prover. So please, Jesper.
Thank you, Lars.
They're all yours.
So I'm Jesper Karlström. I'm in charge of project delivery at Prover. I've been working with Prover since 2008. What we will do today is a demonstration of the full Prover Trident process, the process as we recommend for interlocking design automation. It will not be so many slides, but rather a more hands-on demo of the tools. In the end of this webinar, we will have some recommendations for you, how you can start a journey of automation in your processes. And also there will be a questions and answer session in 30 minutes from now, more or less, as Lars pointed out for you. So post questions in the text box while the webinar is going on, and we collect them and read them loud in the end. And also we will provide some answers to them also. For this demonstration, we have created a little mock-up project, you can say. There are some signaling principles that are not used anywhere in the world as they are, but on the other hand, they should be easy to understand for anyone. I'm just displaying here a few signaling aspects because it's easier to understand for you what's going on if you know what they mean. Each signal here has a light at the top and at the bottom. The light at the top can have 3 different colors. It should be interpreted as some kind of main signaling lights. Red means stop, yellow restricted speed, and green is an unrestricted speed. Then at the second row, for the unrestricted speed, there is also a distant signaling aspect, where red means that the next signal is at stop, yellow that the next signal is at restricted speed, and green that the next signal is at unrestricted speed. As far as I know, these colors aren't used anywhere in the world in precisely this way, but I hope it will be easy to follow with these quite simple principles. The contents of the demo here will be mainly focusing on the specific application process. So assuming that you already have something generic made for your signaling system and you have a new station and you want to create an interlocking for it, how do you do? It consists of first configuring a station with these mock-up signaling principles. I will show you some simulation we offer in the tools, both interactive simulation and scripted simulation. We also have formal verification built in and code generation. I will then show how you can certify an interlocking software that has been developed in this way. And in the end, I will give you some hints on how to make a generic application, how you implement the signaling rules in the language we offer. This demo will have its bias towards the specific application process, and it's partly because we need to pick something for a webinar, but also because the signaling application process is the one you repeat over and over again. So this has to be really simple and to be a really good process in order for this to be a successful way of working. The generic application process is something you do more or less once, with perhaps a few updates now and then, while the specific application process is made over and over again. I like to say also that for most new customers we have had, it's very common that Prover will offer not only tools but also a generic application development as services, while the customer itself handles the specific application process. Eventually, with a more mature customer who are more familiar with the tools we offer and the way we work, the customer can take over the generic application process and do it on their own without our support, with perhaps only second line support from us. With this said, I'd like to start a demo right away. So I close PowerPoint for the moment, and I will open up a Windows application we offer called Prover iLock. So you start it like any Windows program like this. And now I want to show you how you can start, how you can create an interlocking for a new station. You click here for a new project, and you can name it. I will make a small siding station, so I call it just siding. I choose now to put it on the desktop. And then I'm supposed to choose here some signaling principles. And this is now a demonstration project, so I choose demo 211 here. I'm clicking here now, the project will be set up for this generic application called demo. So it contains some signaling principles and also some choices of symbols and everything. So the only thing I need to add now is what is specific for the specific application process. In this window, we have the opportunity to enter some metadata like a project version, a customer creator, and so on. I will not do that now, but for real projects, it's often useful information. It also lists here all things it has loaded. I chose here the demo principles, which ended up here with a version and the location on my hard drive, and also a fingerprint, so I can check, or rather the tool will check that nothing has been compromised. This demo package, it loads other packages, and you can see the list of all packages loaded here with a similar information, version and fingerprint and so on. Okay, let's start with configuring a little station. You do that much as in a painting program. Choose a track, and I don't want to click too much, so I use this feature, repeat new object. Choose a track, and I can draw my station like this. So I draw 2 tracks, and then from here I want to create a switch here, and from here I create a switch like this. Okay, and there is a possibility to rename the switch, but it also has the default naming like this. Now I put out some joints. It's supposed to be isolation joints between track circuits here. You see also here a little name coming up, and I don't care much about names here, so I accept the default names. But if you do have other names, it's just a matter of changing it here. So we have the isolation joints, and I now put out some track circuits. Like this. Now it's time to put some directions. Usually these are not needed, used a lot, but somewhere it's required to have some names on directions. It can be more or less anything. Often it's the neighboring station. And for interlockings with several controllers, we usually put out the names of the different controllers. But for this demo project we can use only one controller. Now let me put out some signals here. Need an entrance signal from this direction, like this, an exit signal here, another exit here, an exit here, an exit here, and an entrance here. Okay, and I don't put any dwarf signals here now. I saw that this wasn't put exactly where it belongs. You can see the little red dot here, and it's a bit off the joint, so I move the signal to the joint like this. Now it should be better. And I save this. Okay, I have now added configuration data for the track layout by drawing the track. And for these demo signaling principles, everything, all information needed comes from the track layout. In many concrete projects, there are other types of different information that are added by configuration tables. But in this case, the track layout only should be a good basis for actually computing the software code for the interlocking. So to do that, I click here, and it will start a computation, taking all the generic principles that we have added before this webinar, the demo principles, and then taking the track layout I just entered here, and it will compute all how this concrete interlocking must work based on this input. It opens a new window here for a simulator. Normally I use two screens, so I have this on one screen and the canvas on another one. Here in the webinar we have only one screen, so I choose to hide this one behind the canvas. You can see now that the signals here have been read. It looks like everything has started. The switch is straight here. And I can now try to use this one by right-clicking on a signal and send some simulate some send request to from the office system to the interlocking. So perhaps I want to request this route. I click here, and we can see an arrow blinking for the switch is thrown. Then this route is locked, and the signal says proceed with a restricted speed. Restricted because it's over a reverse switch. This is an example of something that has been generically defined in the generic application. Whenever there is a route over a reverse switch, it will be signaled with a yellow aspect. If there is no switch or only straight switches, the aspect will be green. So for example, if I have a simultaneous entrance here, on this one, we can see that it is green in the main signal saying you can proceed with an unrestricted speed, but then red because the next signal is at red. We can try to run a train here. Like this, it will simulate a train movement. And I request the exit route. So we can see here that the train is moving. Now the route has been released and the switch is thrown, and now this is green here. And now also the distant aspect here of the signal became green. So this is how it works. This kind of simulation that I use now is called ad hoc simulation or interactive simulation. It's it's a very common way to simulate and test interlocking systems. The problem with this is that you need to have a very systematic approach, going through all the combinations you think you need to test, and also it takes a lot of time because it's manual work. So an alternative is to close this interactive simulator and use a simulator that runs predefined test cases. So I can open the simulator module, and I have a lot of test cases here. They are organized in trees, but we have test cases for routes, and there are 3 different ones here. So there is one test case called RT010 to test that routes are released correctly after traversal of a train, is the informal description. And here is to test that parallel non-conflicting routes are available when a given route is locked. This implicitly includes testing the transfer of flank and front protection functionality. Under these things here, you find the test executed for each route that has been constructed based on what you draw. If you want to run all these tests, you click Run, and it will run all the tests. It's very quick. It's actually, it says it's 0 seconds, not really true, of course, but in a split second it's done, so it's rounded here to 0 seconds. It's quick because it's scripted and it doesn't run in real time, but in a fast forward mode. It also utilizes all the cores of the computer, so it can run several tests in parallel. Another technique that is very useful for verification and validation is formal verification. We have here a lot of safety requirements. The first one says that if two different routes include fully or partially a common track, these 2 routes are never being locked simultaneously. This is just an example. An advantage with the formal verification approach is that when you prove this using mathematical methods, and when you have such a proof, you know that it's true with 100% coverage. When you do testing, you always try a number of scenarios, and you can never do all of them. You pick a number of them, and eventually you rely on that you will not find anything more you need to try. But with formal verification, it's like in mathematics. You prove things, and then you know with 100% certainty that the safety requirement is fulfilled. We have this built into this application, and you can run it by clicking Run. So again, 300 requirements here proved in 0.28 seconds, a really quick procedure. All green. If there would be any violated requirements here, they would turn up red here instead. But here we can see everything is valid, nothing is falsified, and nothing undecided, so it succeeded in proving everything. Okay, I actually showed you everything that is in here for VMV activities. Now when we know that the simulation has passed, meaning that the interlocking will be functional, and the verification has passed, meaning that the interlocking will be safe, we can generate code for it. And for this, in this demo project, we use C code. Although there is support for many other hardware platforms, so it need not be C code. It could be many different software languages. We click here, and it generates a folder here on my desktop where I put the project. And within this folder, there's a C code folder with all the generated files like this. Okay, now how do we trust this now? This has been generated by a Windows program, and we don't really know what has been going on. So we need some kind of certificate that this is trustworthy and can be used in real projects. To do that, we say like this: the formal verification built into ProVerilog, as I've shown here, is very handy but difficult to trust because it's a Windows program and it relies on Microsoft Windows, and no one really knows what's going on in Windows. It's also it is built into a rather complex program. So to ensure that this is now trustworthy, we prefer to run a standalone program called Prove Certifier. I'm about to show you how this is done, but to do this, I need to generate some data that this program will have. to know about this station. So I click here and then generate certification data. The certification data for this station is essentially all the configuration parameters that have been extracted from the track layout. It has to be validated somehow. This is the list of all the variables used by the program. This also had to be checked that it's all the variables, inputs and outputs, for example, are connected to the right slots of the external world and the right equipment. This is just some help file that you don't have to check. This is more or less the same, and here are the generic safety specification that you need to review, and you review it once for the generic application, but it's the same file for each station. So when you have it reviewed and approved, you don't have to check it over and over again. Okay, so this has been generated now, and I also generate a dump of the logical model that we have been using. I do that because we will need this dump in just a few minutes, and I'll get back to you about that. To sum up before I go on here, we configured the station by drawing a track layout, and in this simple demo we only use the track layout as configuration data. Usually there are also some tables with configuration data, typically the kind of data that cannot be represented in a visual manner. It can be the number of seconds for a release timer, or it can be similar things like this. Some choices you have made, for example, not possible to derive from the geographical aspects. Then I demonstrated simulation, both interactive simulation and scripted. And I'd like to stress that it's very important to have good simulation support in order to discover unfortunate choices early. It's not uncommon that you think when you create the configuration of a station that you have made a good choice, but then by simulation you can actually discover that you need to put in a new track circuit, or you need to move a signal or something like this to get better capacity. And you also find mistakes, of course, simple spelling mistakes and things like this. For formal verification, it's a mathematical method to ensure 100% coverage. So you prove your safety requirements with a proof engine that is built in, also done only with a click of a button here. This is a very good way to discover safety critical errors already at the desktop. So you don't need to finish the process and discover errors very late in the process. You can, the engineer who draws the tracks can already himself run the formal verification to check that the solution will be safe in the end. And finally, code generation. The certification flow now, the one that is supposed to guarantee that the interlocking we created will be safe in the end. It has this architecture. We use two different sources for the code. Normally the first source is generated source code, like the C code we generated now, or it can also be imported code in cases where we don't generate code by Interlocking. We have been working with cases where we have a code that has been created manually or by other means, and customers only want us to formally verify that this is safe. And then you don't have to use generated code, you can import code. The other source for the code could be perhaps compiled binary code that's supposed to be run by the interlocking platform, or just a logical code model, as it will be today. You might remember I dumped the code model to have as input to the certification flow. Then we have the safety requirements. It was the file that I stressed is reviewed at the generic application level. And finally, there's the configuration data, which has to be reviewed or otherwise proved to be correct on the safety application, on the specific application level. This is what you feed to the program called Prover Certifier, which is a Linux-based program, and out you get the results saying that the interlocking is safe or not. I want to demonstrate this to you. It's a Linux program, so it has to be, we need to open some kind of Linux terminal. And here I have a Cygwin terminal. Cygwin is a Windows program that can emulate more or less Linux interface. I need to transfer all the files to a real Linux computer. I visit here the folder where I have all the files I've created. Then I move the stuff I want to the Linux computer. So I make a secure copy of the C code and of the certification folder, and also of the logical code model dump that I created. All this should be now transferred to the Linux computer. We have a Linux computer that is open to customers, and it's called Prover Online. And on this one, I put everything in a folder called demo. So now the files are transferred, and I can visit this Linux computer. Here is now the folder called demo with all the necessary data. If I want now to run the Prover Certifier tool on this, I have a little shell script here, demo CT, that was prepared before. Usually we always have a wrapper for the specific project to run the certifier flow. I will run this with the verbose flag and saying that we have the C code in here. We have the code model, the system in here, and we have then a number of files with the certification data. So I run Prover Certifier with this data. Done. The result here is success. If you want to know details about this, you're welcome to contact us. It's of course a lot behind here that I cannot talk about today, such as proof logging and proof log checking and everything. I'd like this to be really sure that this is correct in the end. I also want to stress that it might seem a bit annoying to have to work with a Windows computer and then visit a Linux computer and so on. But normally during a project, you work a lot with Prover in Windows, and then doing what I just did here is only something you do once. When everything is approved, the factory acceptance tests have been run and so on, you visit this Linux computer and you run just to be sure about safety once. So in my opinion, it's not a big deal that you have to spend a few hours on logging into Linux computer once per station you actually create. I exit. Okay. Let's go back to this. To sum up what I did here for the certification process, I collected some relevant files here. I transferred these files to a Linux computer. I ran Prover Certifier from the command line. And the only thing that actually remains for this to be the real process is that the configuration data I fed to Prover Certifier has to be reviewed. It's about checking that the configuration data agrees with the reality. So if it, for example, says that the route between the entrance signal and the next signal contains a number of track circuits, then you need to check that this is actually the case in reality too. Checking configuration data is something that you can never skip in any process. So this is something you must remember. It always has to be done. And the certification process here is only used as a sign-off final step just before safety approval. It's more handy to work in ProViloc in the Windows program over and over again, but to be absolutely sure, it's worth logging into a Linux computer in the end and run the certification process. So far, I have touched only upon the specific application process, and for most of you, you will probably only work with this specific application process. I've seen a bit who is currently participating, and I know that many of you work only with specific application processes. I do think it's good to know a bit how the generic application process is done anyway. So I suggest that you still pay some attention to this. And for those of you who will actually work with the generic application process, I hope this is a good introduction to how to do it. I need to exit because this was the summary of what I'm about to do, which I haven't been doing yet. It's a bit too much for demo to start a generic application from scratch, but what I think I can do is I can make some changes. I ran, if you remember, the simulator, and I ran also the verifier before, and it's all green. These are two different things. The simulator being green means that the interlocking is functional, and the verifier means that it is safe. What I'm about to do now is to change the definitions a bit. So I will first make a change that will make the interlocking less functional, and then something that will make it less safe. So I visit all my packages here. I think we have it in here, demo design 211. I choose to open the definition of the behavior of switches. This is an example here of how a switch is programmed. So a quick overview for you to see how this is done. We use a logic language that is called PySpec. It is based on standard things like predicate logic that is taught in university courses all over the world. Besides this, we have designed this language ourselves because predicate logic only is a bit theoretic to use in reality. You need some other measures to ensure quality. So, for example, we have added some types. So you can speak about track circuits, and you can speak about routes and things like this with different types, which is very handy. What I would like to show you now is if I make a little change here. Sorry, I close this one and I make a little change. Say I introduce a typical error here. We have a function for throwing a switch to the left and a function for throwing it to the right. A typical error would be to have a copy-paste error here. So I can add left by root, introducing an error by purpose, and the task now is to find this where it occurs. I think we need a little overview here to understand what's going on. The logic here for throwing a switch left is it checks 5 different things. It checks that the switch is not locked. It checks that this is a not symbol and this is an and symbol, I forgot to say. It checks that the switch is not locked. It checks that the switch is not already placed to the left when we start. It checks that there is no request from the human machine interface to throw the switch to the right. This would prevent the switch from being thrown. It checks that there is no route that requests the switch to the right. And then if all this has been fulfilled and there is either a left request from the human machine interface or a left request by an automatic route, then the switch will be thrown left. I didn't touch this, so this should still work, but I did touch this one. It's the analogous thing for throwing the switch right. I introduced left here instead. Let's try to open the project now after having introduced these changes. The first thing that happens now is that we get a warning that things have changed. It says that this file, the one I changed, is not correct anymore. Because as you might remember, when we opened the project, it gave us a fingerprint, a checksum. And now the tool discovers that the checksum is not correct anymore. The file has been altered. It also finds a file here that is some kind of auto-save file from the editor, which doesn't belong to the package, and it warns about this. We just ignore this now because we made the change by purpose, but it's a good watch against changes that you don't want to have in your packages. Okay, let's now run this. We start the simulator. Click here, everything is computed, so based on this track layout and based on the generic principles that I just changed, the interlocking principles are computed. And now if I run the scripted tests, it will turn out that some of them are still green, but some are now red. If I open up more, I can see that most of them are green indeed, but some are red. So I can double click on one of them to try one and run it. It explains here what it does. It starts the test by waiting 60 seconds. It then checks the number of things and makes some actions. And when it comes here, it fails to lock a route. So this is the situation we have. We have requested a route, but the route never gets locked. I can try to repeat this to the interactive simulation. Start the interactive simulator. And first I try this one. Request this route. The switch throws to the left as it should, and the route locks. If I now release the route, sorry, let's have this one. We have a manual release procedure. The switch was thrown to the left, and as you might remember, I didn't change the throwing to the left at all, so I actually expected this to work. Now I request the route here instead, and as you see, the switch never throws, so the route will not lock. But if I send, and this is because I changed the logic to introduce this error. If I send the manual request of throwing it to the right here, the switch will still throw because I didn't change that, and the route locks. But this explains why we have failing tests. If we care about safety only, we run formal verification. And it turns out that all the safety requirements are still fulfilled. The interlocking did not become unsafe because I introduced this. If I try to use a route, it will not lock because the switch will never throw, but it will not put any people in a dangerous position, which is good. This demonstrates that some errors can be found by simulation that isn't found by formal verification. But I'd like also to show you the opposite. So if I restore this, right, and we visit something else that is more safety critical, like the equation for locking of the switch, here it is. We can see here, when is the switch locked? Well, when a track over the switch is not vacant is the first one. So the idea is that if you put something on the track, it should not be possible to throw the switch. Then the second option here is when the path over the switch locks it, simply because it's a locked route, for example, then the switch is kept locked. Then there is an option for flank protection and one for front protection here. But if I take away the stuff that actually checks that the switch is vacant before throwing it and saving like this, then so I restore the old error and I introduce the new one. Then let's see what's happening. We get the same warnings about changed things. I ignore that and I start now the simulator. Clicking here, again, all the configuration data entered here will be used together with the generic application principles to compute an interlocking for this specific station. Now, if we run all the test cases, these pass. But if we run instead the formal verification, we find some requirements that are not fulfilled here. By double-clicking on them, I can watch a bit more. It displays here the requirement in ladder logic. We can see here that what happens is precisely that it's not guaranteed that track S2 is vacant when the switch is thrown. So let's look at that. And I can close this window. Here, switch S2 is not guaranteed to be vacant when this is thrown. This is what we found. We can reproduce it in the interactive simulator. If I put something here and I throw it, it's thrown, which it shouldn't be, but it's because I changed the lines here. Okay, let me restore this. Here we have it, restore it. Okie doke, and then close. And let's open again to see that the warning disappeared. I think we might have one other warning still because of the auto-save data. Yes, the auto-save data is still there, so let's clean up this file and reload again and see that the warning is gone. Yeah, now it's gone. Okay, so what did I do? I changed some signaling principles just to show you how you can investigate the impact of such changes. First simulation showed how a small change turned out to have big unwanted impact. So I introduced a little copy-paste error in the throwing of the switches to the right, and many test cases fail. Then I restored this and made another change, and now formal verification showed problems instead. So this is often the case. There are kind of complementary simulation and formal verification. I didn't focus a lot on the generic application process today. I would like to say that it's in fact not a big difference process-wise compared to any generic application process. The main difference is that you work with predicate logic, which is very powerful. So in many cases, this has a lot more expressive power than other methods. The key to have a successful generic application development process is to have a good specific application process so you can try all the time what you do. Some recommendations now if you want to increase automation in your process, whether you use our tools or tools from someone else. It's very important to integrate tools as much as possible. We see processes that are more or less good, but the problem is that many different tools are used, and the transfer of data between these tools are not easy. If you integrate tools, if you try to do some code generation without good V&V support, like simulation and formal verification, experience tell us that the result is often poor because you don't discover errors until very late in the process. Then by having integrated tools, you can make V&V tools available to all involved engineers. So already the ones who are supposed to do design can run simulators and formal verification and discover issues early when they have the chance to correct it, and before corrections become very expensive. Another recommendation is bring your staff on board. A very common question we get is, what do I do with all the staff now that would be without jobs if we buy these tools? Well, this is not really the case. For railway, there is a big demand. So experience says that if you invest in good automation, you can still use all your staff. You can simply do more instead. Let engineers, senior engineers, work with the generic signaling principles, which is often challenging and fun for experienced people. And you can use more junior staff on drawing things and configuring things. If you use staff in this way, you can deliver more with the same staff. To start generic application development, you need some kind of specifications for the line you want to signal. As you might have, I hope you understood when I made the demo that the choice I made in the beginning of the demo principles, it decides which signaling principles will be used and all the symbols and so on. So somehow we suppose that for a line there are common principles. You need some kind of specifications. This could be discussed a lot, but briefly, an object model is an overview of all the objects used and their interfaces, such as inputs and outputs. You need a very precise specification to settle the terminology and have good understanding of the environment where the system is supposed to be used. Then for the design principles, it's good to discuss early the fundamental principles, such as in our country, we always require that switches are in the correct position before the route is locked. Then this should be specified in the signaling, in the design principles, and it should be strictly specified. Details can be left to an agile development. We also need some tests specification. It's good to make them early because then tests can be used for test-driven development, which is very efficient. Also as a way to communicate with developers how it's supposed to work, and safety requirements that we can do formal verification with. An option, if you think this is complicated, is that you let us write the specification. We have done that for many customers. We usually then start with example programs, drawings, and whatever you have since earlier. We will need from you probably an expert who can answer questions we will have along the way. And then we start formalizing the specification. So again, you need an expert on your side if we are supposed to do the formalization for you. Because when you formalize things, you always discover ambiguities that have to be resolved. So it's very good to have a senior engineer to call in that case. The first step for you, if you want to increase automation in your process, would be to have a meeting, perhaps via Skype or face-to-face with us, 1 and 2 hours. During this meeting, we review together your current processes and your challenges you have. And it's fair to say that in the end of such a meeting, you will have a plan for how you can increase automation in your process. It doesn't take a lot to hear what the obstacles are in your current process. If you want to get inspired and understand more about what we offer or what you could do as an alternative to that, we could have an interlocking design automation inspiration workshop for further knowledge about the Prover Trident process, as I just gave a demo of. And we construct together a roadmap for you how you can change your current process. If you are more interested in a business case, we can arrange a business case workshop, estimating together what you would gain from automating things, discussing break-evens and so on, and compare various options for you depending on your needs. Yeah, actually, this was everything I had to say. So let's start with the questions and answers session. I hope Lars can bring some questions.
Yes, we have some questions, and we have some time for answering some questions. We have at least some 8 minutes. So I'll read some of the questions to you, Jesper. We'll see how you can answer them. The first one: do you have or normally run a test that verifies any given control or input so it doesn't have an undesirable effect on other part of the interlocking?
Some kind of, I see. We don't have any kind of general solution for that, but several customers have safety requirements like this. I think I need to know more about this in order to give a good answer, actually, something more concrete. It's a bit difficult.
Yeah, so send an email to Jesper afterwards.
Yes,
so you can
please.
set up a specific call about that one. Okay, we have another one. Can iLock or Prover iLock automatically read in structural data and topology from XML files?
Yes, this we have actually done. In that case, a customer had an XML format for this, and we got the specifications for this, and we implemented something. So it is possible to import topological data from XML, but we will need to make some work around this, depending on the format.
Okay. Could you briefly say something about the theoretical concepts and methods behind the formal verification? Would reasoning in higher order logic add anything to your methods? You understand the question?
Yes, I do. I don't think so, actually. There are usually there are two different attitudes towards formal methods. One is more based, traditionally at least, on higher order logic reasoning, but then it's more what we call a proof assistance. So you need to have some interaction with a human being to prove things. We have chosen to have a fully automated pipeline, and then propositional logic, as we use, or temporal propositional logic, is more efficient. So this is what we have been focusing on. Again, you can send an email if you want more detailed answers.
Yeah, and you can have a separate discussion. Right, we have a pretty straightforward question here. See if you can answer this one. Which hardware platforms are currently available? You talked about hardware platforms, but you never mentioned which ones.
Let me see if I can come up with a list here. I can give you some examples at least. We have been working with Microlock, VHLC, Electrologix, Westrace Mark 1, Westrace Mark 2, IVPI, Melock, Tempo. Yeah, I don't know from the top of my head. I've probably forgot someone.
Yeah, we have another question that is, I think you kind of already answered it. Does Prover link to common hardware used by Class 1 railroads, GEO, Electrologix, IVPI, Microlock?
Yes, we actually have one of the Class 1 railroads as a customer since a long time. So this I know for sure.
Okay, good. All right, here another pretty long question. The compilation of code seems generic and more applicable to test out of software on the bench, but there must be some form of integration with the actual hardware being employed. and it's caveats.
Okay. Yeah, I'm not sure I fully understand, but perhaps this is the answer you're looking for. We don't connect to hardware at all. What we do is we need a model of how this hardware works. So in the simulator I showed, you need to choose a hardware platform to get a simulator that behaves as this hardware would do. So all the ones I mentioned before have been supported, and we do the same with a formal verification. So you actually specify what kind of hardware you intend to use with this, and then you get a faithful simulation or model in this way.
Okay, we have a couple more questions, and we have another at least 3 minutes. So I hope we'll be able to answer all of them. What national regulatory approval bodies have so far accepted the ILOC certification as a valid component of the railways and application safety case for an installation?
Yeah, the first one in Europe using these tools for, not Prover ILOC actually, but Prover Certifier for in SIL4 environment, so the highest safety requirements was RATP, the Paris Metro, and they still use it for many lines, a bit dependent on who is the supplier for the moment. Then we have been using it in for SL in Stockholm, the same level. So these are the ones that have been using in Europe. Our Prover Certifier for proving Senelec SIL4 requirements.
Okay. Are there capacity limits to the system with respect to the complexity of the model installation? For example, maximum switches, signals, routes, stations, and so on.
We haven't tried, we have tried, the biggest ones we have tried was one station with 75 switches and one with 200 switches. And it worked. It took much more time, but it still worked, at least that I know.
Okay, we have, I think we have time for one more question. It's 2 minutes left until we have to end the webinar. How is this different from existing simulator tools employed with a hardware package?
The simulator is perhaps not so much different in itself, but the main point here is that there is no hardware attached, meaning that if you have 20 engineers working on a project, each one will have the simulator in his own laptop. So you don't need 20 pieces of equipment to connect to. You can have it in your laptop and bring it home if you like, and so on. So the simulator is much closer to the software developer and not something specific that you do in a specific lab or something like this.
Okay, so if you haven't been able to get your answers for the questions, please don't hesitate to contact Jesper afterwards. You will receive an email with contact details and information, and with some links to some useful information that Jesper talked about in the end of his presentation. It's now 4 o'clock Central European time, and we have to end this webinar. Thanks to Jesper, of course, but a very warm thanks to all of you that attended this webinar today. So thank you so much, and we'll stay in touch. And check your mailbox for the follow-up email after the webinar. So thank you and goodbye.
Bye-bye.